In the last lecture, we were looking at this idea of what can and cannot be learned using using this tool of called measuring sample complexity. And I mentioned that there are certain classes of functions that can be learned. So what I mean by that is for certain classes of functions, in particular, let's take the example of conjunctions. The argument was for conjunctions, the only complexity parameter that we need to calculate is what's the number of functions, what's the size of that concept class. So if the concept class C is, let me just pull up a new, if the concept class C is the set of all conjunctions. In the last lecture, we saw that the size of C is 3 power n, where n is the number of features. And the Occam's-Razor theorem says if we have m greater than 1 over epsilon times log size of C plus log 1 over delta, if we have these many examples, then with high probability, with probability more than 1 minus delta, a classifier that perfectly explains the m examples, meaning it's consistent with m examples, will have error less than epsilon. So if we plug in size of C here, this thing becomes 1 over epsilon times 3 log n plus log 1 over delta. And this quantity here at the bottom is polynomial. In fact, it's linear in 1 over epsilon. It's logarithmic in 1 over delta, and it's logarithmic in n. Did I make this? No, it's the other way around. It's n log 3. So it's linear in n. And this checks all the boxes for pack learnability, the definition, because the sample complexity needs to be polynomial in 1 over epsilon, 1 over delta, the size of the hypothesis space, and the dimensionality. And what this means is the set of conjunctions is pack learnable. And for it to be efficiently pack learnable, you need to produce an algorithm that will be consistent, that will produce a conjunction that's consistent. And we've already seen an algorithm that does that. The elimination algorithm that we saw a while back is guaranteed to produce a conjunction that is consistent with the data set. So this part is done. So this is the kind of analysis we can do. We can say that certain classes of functions are learnable under the pack model, and certain classes of functions are not learnable. In particular, we saw a class of functions, we're calling that C again, all Boolean functions. What is size of C? How many Boolean functions are there? 2 to the 2 to the n. And in fact, honestly speaking, I can write the whole thing again and copy this whole thing over, but really the only thing that matters is log of the size of C. So I can just say log size C is log, it's just 2 power n. It's depending on the log base. So let's just make it order of 2 power n. And that quantity is exponential in the dimensionality. So when you plug that into the sample complexity bound, you get something, you don't satisfy the conditions for pack learnability. So all Boolean functions are not learnable. So this is, again, there are certain functions that are learnable, certain functions are not learnable. It doesn't matter what algorithm you use. No matter what algorithm you use to find a Boolean function that's consistent with the data set, even if it finds a function that's consistent with the data set, you cannot guarantee that future error will be low, because in order to make that guarantee, you need to have seen an exponential number of examples. So that's too many. Then we started looking at computational complexity results. But one of the things that I mentioned is certain classes of functions are learnable. In particular, there's this function class called two-term DNF, which I said is has a sample complexity that's polynomial, and which means that only using a polynomial number of examples, we can find, if we find a what's that, two-term DNF that is consistent with a data set with a polynomial number of examples, that two-term DNF is going to have low error in the future. It's going to generalize, which is great. From the sample complexity point of view, this function class is learnable. And yet, from the computational complexity point of view, it turns out this function class is not learnable because finding a two-term DNF that's consistent with the data set is interactive. So while if an algorithm existed that could find a two-term DNF that's consistent with the data set, then that algorithm, if an efficient algorithm existed, then we could use that, we could find a function, and then we can guarantee that this is a good classifier. But actually, that algorithm that searches over the space of two-term DNFs cannot run in a reasonable amount of time. So we have a function. This is a counterexample of a function class where the sample complexity is polynomial, but the computational complexity is, I think in this case, it is NP hard, which means it's harder than NP complete. This is an instance of a situation where the representation we choose matters, because the set of all two-term DNFs, if I draw that using this red circle here, every dot here is a two-term DNF, so I'll call that C, is contained inside another function class, which is called a KCNF, just a different function class. So this is a KCNF, and this one is a K-term DNF, a two-term DNF. KCNFs can be efficiently explored. And so even if you know that your function is a two-term DNF, it's better to search in that larger space. You'll find something that works. You might find something that's outside that, but that's where you might lose a bit. But it's better to search in the larger space. We've already encountered an instance of something like this, where rather than working with I forget the function class now for mistake-bound learning, we can actually use linear classifiers rather than the discrete search to learn efficiently. Combinatorial spaces can be weird that way. This is where we stopped at the end of the last lecture. I wanted to kind of just give you a list of other such negative results. When we talk about things that cannot be learned, functions that cannot be learned, or sets of functions that are unlearnable, there are two types of negative results. Some classes of functions cannot be learned because the sample complexity can be prohibitive. Some class of functions cannot be learned because the computational complexity is prohibitive. And here, when I say cannot be learned, I mean in this consistent classifier setting, in the case where we find a consistent, a model that is consistent with a full data set, and then use the model. So the complexity theoretic argument says that these classes of functions, exploring this set of functions, can be computationally too expensive, so we can't learn them. And usually the argument boils down to this class of functions cannot be learned unless P equals NP. That's like the loose class of arguments. The other argument involves how much information is present in only a finite number of examples. Can you disentangle a model, a classifier that can explain the concept using only a finite number of examples? And the way to think about this is the proof for this typically involves the statement that this class cannot be learned using functions if your learner searches only that set. Maybe it can search a larger set, and maybe it can learn a good approximation, but if it searches only that set, it cannot be learned. The example is, for example, all Boolean functions. So just a quick list of function classes that cannot be learned. From the complexity point of view, we saw this example of a K-term DNF for any K more than one. It turns out there is this neat result from Avram Bloom and Ronald Rivest from the 1980s that says neural networks of a particular architecture with two layers. We've not covered neural networks, but I know that several of you have encountered this before. With two layers, 3 nodes, n inputs, and only threshold activations. Turns out there's a theorem that proves that cannot be learned. And then there are other um, uh, uh, named classes of functions, something called Riemann Boolean formula, quantified concepts. Namely, you have a for all, or there exists a universal or a first or existential quantifier. So first order logic, basically. From the information theoretic point of view, meaning sample complexity is bad for arbitrary Boolean functions. We were able to just prove that. Finite state machines. How many people have seen finite state machines or finite automata? Imagine that I have a finite automaton or a regular expression that accepts or rejects a string. And think regular expressions, because probably many of us are familiar with regular expressions via programming. Imagine that I have a regular expression that can either accept or reject a string, meaning given a string, I can the regular expression says true or false. Now I have a list of strings and true or false. Now the goal for the learner is to recover the regular expression that I am hiding. Turns out cannot be learned. Context-free grammars, if you are familiar with that, cannot be learned. There are a lot of interesting function classes, it turns out, cannot be learned under this model of learning. This is not always a problem because we can learn an approximation. Well, even with pack learning, the idea is that we are learning an approximation, but maybe we are willing to live with large errors. Maybe we are willing to sacrifice that guarantee. And sometimes the theorem just is too loose. And while the theory says something cannot be learned, we might still find a function that is okay. So there's a gap between what machine learning theory tells us and what practice or empirical experiments show. And we'll be talking about that gap quite a bit at the end of this unit on learning theory. This is where I want to wrap up. So the general gist of this is we've covered this idea of the Occam's razor. I've noticed that there are questions, quite a few questions on Zoom. I'll come to them in a bit. So we've been talking about Occam's razor for consistent learners. And this particular theorem is a tool that you can use for proving whether some function class is pack learnable or not. Now, this assumes that you and I and everyone who's interested has agreed that pack learnability is a good measure of learnability. And I think it is, because it essentially says that with high confidence, we are able to discover a function that has low error. And that's about as good as we can do. And there are two kinds of negative. You can prove some function classes are learnable, and you can prove that some function classes are not learnable. When something is not learnable, it can be because the sample complexity is too high, or because while the sample complexity may be okay, there's no algorithm that's efficient that can actually do that search. Remember, learning is search over functions. While if you can't search over that space efficiently, there's no point in implementing that algorithm. Okay, I want to quickly go over some questions in Zoom. Can we have a bonus question? I think, is that for the exam? Maybe, I don't know. Is this a case because of De Morgan's law? So Christian, can you remind me where what was the context there? While you're doing that, I'll answer the next one. What's the range of acceptable computational complexity for something to be pack learnable? The computational complexity for pack learnability is the learner should be able to successfully return a classifier in time that is polynomial in 1 over epsilon, 1 over delta, the size of the hypothesis space, and the dimensionality. It's the same for complexity parameters. It's 1 over epsilon, 1 over delta, the size of h, and I'm calling the dimensionality n now. So it's in the same 4 things. And we want our learner to be to successfully learn it's whatever it does in time that's polynomial in these 4 things for it to be considered computationally efficient. I'll answer this thing on Zoom. A follow-up, there are not pack learnable functions that are learnable. That seems complicated, so maybe you can explain that. Um, there is so with respect to the De Morgan's law, a CNF can be expressed as a DNF. That's right. A CNF can be expressed as a DNF. Any Boolean function can be written as either a conjunctive normal form or a disjunctive normal form, and they are both just universal representations for Boolean functions. Yes. That's the definition. That's just the definition. So if you remember for pack learnability, the definition really had two parts. One part was the sample complexity should be polynomial. In examples that is polynomial in these four things, we need to be able to find a learner. The learner needs to be able to find a classifier whose error is less than epsilon, and it needs to do so with high probability, 1 minus delta. That's a sample complexity. The second part of the definition, which I presented as efficient pack learnability, says it should do all of this in time that's polynomial and that handles this part of it. And that's the polynomial time. And this is the polynomial sample complexity. Yes.
Learnability model that explains those non-polynomial cases?
So there are other more complex models of learnability, but they kind of build on top of this. I mentioned that pack learnability is a measure of learnability, but it's not deterministic. I'm sorry, I'm completely missing the context here. Ghazal, maybe we can take this offline because this is, I don't understand the question. Okay. Are there other questions? If there are not, let's take our first maybe 3-minute break while I switch to review. And in the meanwhile, I'm going to try to understand Ghazal's question.
So they don't stack up.